share a screen.
Yeah.
Okay. I think my screen sharing is disabled.
Ah, 1 second. Yes, I have to. 1 second. This is my fault this time.
Oh, no.
1 second. Where are you? Ah, here. Okay. So now it should work.
Okay, good. Okay, good. Can you see what's on the screen and can you see me drawing?
Yes.
Yes.
Okay, perfect. So I'm not going to read the outline. Essentially, I just want to quickly remind what we did last time, only the essential part of it. And that was, let me just move this thing over here. We looked at the space time or time space, and the mechanical system moves in such a way as to minimize the quote unquote length of the graph. So that length is measured by the integral of the Lagrangian, and we are looking at the minimizing curve, the curve that makes this integral as small as possible, leaving aside the question when such a minimum exists. It does when the end times are near each other, sufficiently close to each other.
I'm sorry for interrupt, but if you are writing now, at least I cannot see. When you wrote before, I could.
This, I wasn't writing, but can you see my motion of the red dot on the screen? No.
I don't.
It's a perpetual problem. You know what probably happens is when let me stop sharing again. And I think when I move from one screen to the other, that's maybe what happens. So I'll try again. Let me do this. How about now?
Yes, thank you.
Okay, great. Learning slowly with the emphasis on slowly. So we are looking at the key concept. It's the main actor in this story. It's the action that is the minimal integral of the Lagrangian between two over the curve connecting two given points in space, in time space. Okay, so we define this action. So it's a function of two endpoints. Each endpoint has two coordinates, one time and the other space. Space could be vector, but we don't have to worry about it now. So let me just say, what is the main theorem that I was talking about all the time, and what's this main observation? And here it is. So we again consider the action between two given points, T0, X0, and T1, X1. That's point we call A1, and this is our A0. And we look at the minimizing curve and define the action between these two endpoints as the integral, or rather minimal value of the integral over all possible connecting curves from T0 to T1, just to write the whole thing, L of X of T X dot of T dt. Just to record what I had said, X of T0 must be fixed as X0 and X of T1 must be fixed at X1. So this is the main concept. And so, like I said last time, we can think of this S as kind of the analog of the potential energy of the slinky that you're holding by its two ends. And we could ask the same question: what's the force on the ends of the slinky? In other words, what is the gradient of this function S with respect to the endpoints? So here's the theorem, whose proof takes two lines. And it says that gradient of the action, it doesn't matter which point we take the gradient with respect to. So let's, for now, think of this as fixed and A1 is variable, right? I mean, there is this symmetry, so if we take the gradient with respect to the other point, we'll know what it is. It's going to simply be the same thing with a minus sign. So anyway, gradient of S with respect to the, let's say, right endpoint, which means by the gradient, I mean simply partial derivative of S with respect to T1, comma, partial derivative of S with respect to X1, right? If X is a vector, then this is a gradient. So then it would be of dimension equal to the dimension of this configuration space. Okay, so here is the theorem. Here's the statement. The time derivative, if you vary this endpoint by X, here's it turns out to be the Lagrangian minus X dot L sub X dot. So that's the T1 derivative. And what I mean by L, of course, you evaluate L at this value of X and at this X dot, right? So X dot refers to the derivative of this minimizing curve, right? And for the second component, partial derivative by X1 equals simply L differentiated by X dot. And this is at T equal to T1, of course. So that's the main theorem. So now I want to see how the consequences of this theorem come out. So in other words, this is S1 and this is, okay, you know what I mean. This is the derivative by time, and this is the derivative by the position. Okay, so we have, let's summarize what we have. We have a function L is what everything started with. The Lagrangian is the given function. Everything came out of it. In terms of the Lagrangian, we defined the action as the integral of the Lagrangian, and we discovered that the derivative of this action is given by, in terms of the Lagrangian and the minimizing curve. Now, we could use, now here's how does the Legendre transform come in? Well, you already see this is the expression we defined H by, right? The Hamiltonian was defined exactly by this, except for a minus sign, right? Recall that in textbooks, or one always defines H as X dot L sub X dot L. Right, that was the definition of H I described. Okay, so for historical, yeah, and we also defined the momentum. I should have said that first. The momentum is defined, before we discussed any of that in all textbooks, they defined the momentum as the derivative of the Lagrangian by the velocity. So you see, we don't have to know any of that. We simply could have asked this question, what's the derivative of this action? And these expressions simply pop out automatically without us having to invent anything. And now, when you look at this expression, at this, what is the most convenient way to parameterize this? You see, this guy, L sub X dot, comes in twice. So it looks natural to, instead of X dot comes in only once, but L sub X dot comes in twice, so it's natural to define Lx dot, use Lx dot as a parameter, call it P, and this depends on X and X dot, right? So instead of using this X dot as a parameter, we use P. And then we define, we give this thing a name. You see this gradient, this expression, is completely known if we know this vector or this number. Let's say if X is a scalar. If we know L sub X dot, in other words, we know this thing, then we know this obviously, and we know x dot because we can solve. So what I'm trying to say is that, you see, there are motions, not just this, there are different motions that end up at this point. There are different possible trajectories that pass through this point. So x dot is can actually be different. It depends on the left endpoint. So we should not think of x dot as given once and for all. When you're at this point, you can have different x dots, right? So it should really be a parameter kind of. So not just this, there are different motions that end up at this point. Okay, so anyway, so we defined, we call this P, and we define also this first component then becomes, so let me say L minus x dot Lx dot becomes a function of P, right? Because we, so it's L of xx dot, which depends on P, right? Minus x dot, which depends on P times P, right? Anyway, so we call this, for historical reasons, this is called H of x of P, but with a minus sign, right? So that's how the Legendre transform comes in. We simply recognize the Hamiltonian and the momentum. And geometrically, I just want to say, this is kind of nice. Let's look again at this picture, time and space, and fix the starting point, A naught, and look at different trajectories that come out of this point. So these curves are minimizers with different endpoints, right? And now I want to look at, so I look at different trajectories starting out, and I want to look at the points which cost the same to get to. In other words, if I think of this action S as the distance from x naught to, from A naught to A1, let's look at the equidistant points. It's kind of like a circle, right? In this quote unquote metric, right? So let's look at equidistant points, and I'll just draw a curve. And if you look at trajectories connecting A naught to this curve, all these trajectories have the same integral of L, the same action. So this is, in other words, the curve where S of A, so this is the point set of points A1 for which S of A naught to A1 is fixed. Okay. Then what does this gradient tell us? It's the normal vector to this kind of wave front. So in other words, I should draw this again. The normal vector gradient of S with respect to A1, this is point A1, gradient of S with respect to A1. Here's the picture, gradient is perpendicular to the level curve. And to put geometrical meaning into this theorem, the T component of this gradient, this is the Hamiltonian, well, with a minus sign, and the X component is the momentum. So we get this geometrical interpretation of the position and moment of the Hamiltonian of the momentum. They're just the T and X coordinates of the gradient of the action. And intuitively, you can think of it as a, well, as an analog of the force acting on the end of the slinky. When you hold the slinky in equilibrium, and it minimizes another integral. So these two concepts, H and P, are just like force in the T direction and the P direction. Okay, so that's one consequence. We got Legendre transform simply falls in our lap. Here's another consequence, the Hamilton-Jacobi equation, which I never mentioned, but you could ask, so let me just write this again. So the gradient with respect to the endpoint is L minus x dot Lx dot minus comma L sub x, which I can also write as H comma P. Well, to be honest, minus H comma P. Okay, so what does that mean? That means that partial derivative S with respect to T equals to minus H of X and P, T comma X, right? S depends only on T and X. And where P is S differentiated by X. Why is that so? Well, because of the main theorem, right? That's what this is S sub T. The gradient is S sub T sum comma S sub X. This has to be equal to that, right? So in other words, we have S sub T. So I'm simply substituting now. I'm done. Equals to minus H of X S sub X. This is, we discovered that the action, we don't know what this action is. I mean, it's a very complicated thing. You have to take a point and find the minimum quote unquote distance to that point from the starting point, right? That's what the action is. You could have started a different point. That the action depends on the two ends, right? So one could ask, what is a characteristic property of the action? If you're given a function, could this function be an action? Could a function S be coming from some Lagrangian? And the answer is given by this equation. It's a characteristic property. Any action must satisfy this. Let me give you an analogy, okay? So here is an optical analogy, just to give it a feel. So in optics, consider a medium, let's say in the plane, right? The plane is like inhomogeneous optical medium. So the speed of light varies from point to point. Medium planar with speed of light given varying from point to point. So the speed of light is c, and it depends on the coordinates x and y, right, in the plane. And let's say we have a source of light at the origin, it flashes, and the light travels, and at some time t, the light reaches, this is the front of the light, right, the wave front. Let's call time t of xy is the time to get to xy. It's for the time, the light doesn't have to go in a straight line because the medium is inhomogeneous. So so for any point xy in the plane, I simply compute how long it takes to get there. This is just the set of points for which it takes the same time to get. What is, I could ask, what is the characteristic property of this function t? It turns out that the fact is t of xy satisfies this property. Gradient of t has length equal to given in terms of the speed of light. It's 1 over the speed of light. It kind of makes sense because why does it make sense? If we look at a trajectory of light, here's the time t, and here's the time t plus delta t. And I could ask, let's say this is x and this is x prime, and how far these 2 points are. So the distance between the x prime and x is the speed of light times delta t, right? And so delta t divided the change, the difference in time between these 2 points, which is delta t, divided by the distance, which I call delta x. All right, delta x is this distance. Oops, I'm so sorry. Delta x is this distance, equals to 1 over c, right? And that's basically, that measures the gradient of t, right? So this is called the iconal equation. You see, it kind of makes sense. If the light is very slow, then this is a large number. C is small, it's a large number. Gradient of t is large. What does that mean? That means that if you look at the wavefront at consecutive times, these are very closely spaced together, right? Because the light didn't go far enough, and that signals a large gradient. So intuitively, this equation makes sense. Anyway, so my point is this. So you see, this optical situation is extremely analogous to the one we considered, because here we have 2 points in physical space rather than in space-time. We have the minimizer of some kind of length, which in this case simply is the time of travel. And this gives rise to the function t of the point, which is kind of the cost of getting to the point xy. And the gradient of that cost is given in terms of the properties of the optical medium. Look at the Hamilton-Jacobi equation, it's extremely similar. S was almost a verbatim the same kind of thing, right? S was how much it costs to get to the point A1, right? And this equation also puts some kind of a restriction on the gradient of S, right? It's S sub x, S sub y are the 2 components of the gradient of S. And well, it's not as beautiful an equation as this. Here is just partial by x squared plus partial by y squared square root. Here it's something more complicated involving the given function h. H is given in terms of the Lagrangian, but it's a known function. So it's some kind of so just maybe I will not give an example because that doesn't really clarify anything. I want to just say conceptually, Hamilton-Jacobi equation says that the gradient of the action must lie on a certain curve, basically, just like in the optics, gradient of the time must lie on a circle of a radius 1 over c, right? Here is going to be some other curve. It's not a circle, but the same kind of thing. All right, so that's all the Hamilton-Jacobi equation. I probably should mention the generating function. So here's the again, the generating function. Again, if one reads texts, even Arnold's book, it is not that clear how these functions come up, but in this picture you will see immediately what they are: generating functions. You know what, let me actually, I apologize, I jumped ahead of myself. Maybe the next thing I should discuss Noether's theorem, how it comes out of the picture I just described. So what Noether's theorem says is that if the mechanical system has symmetries, I'll say more specifically, then there are conserved quantities. For example, if the Lagrangian is invariant under translation in time, which in our case has always been so. So our Lagrangian, so let me case special example one rather than case. Example, instead of stating the theorem in the general case, I will just say example one. L doesn't depend on T. Of course, if x and x don't, if x is a function of time, then it does, but apart from x, it doesn't depend on time. For example, we could have a Lagrangian which also does depend on time. I never discussed it, but so that implies, what does it mean? Let me just draw a picture. So here's our t and here's x. And let's take 2 points again, as I had before, A0 and A1, and the minimizer connecting A0 and A1. And now what happens? So this minimizer is basically the integral of L of x dot dt, right? But from T0 to T1. But what happens if I just take these two endpoints and move them over by some parameter tau? So let's advance this point by distance tau in the t direction only, and the same with the other point. Then, of course, we'll have a congruent minimizer, right? Here I'm using the fact that there is no t in the Lagrangian. In other words, what I'm saying is the action between, I'm not writing x1, so the action depends on t and on x, but x is not changing during this translation, so I'm not even mentioning x. So it's s of t0 and t1, that's the original action along the first curve, and then the action along this is going to be the same. So it's going to be s of t0 plus tau, you see, and t1 plus tau. In other words, if I translate both times, I do not change the action. That is pretty straightforward. Now, this is for any tau. So let's take a derivative with respect to tau. So we get 0, take dd tau. 0 on the left-hand side, because there is no tau there. On the right-hand side, we have s differentiated with respect to t0, plus s differentiated with respect to t1. And let's take derivative and set tau 0 after taking the derivative. Well, this is the conservation. This is a statement of conservation of energy. Because what was S sub t? So by the main theorem, recall instead of scrolling up, I'll say recall that S sub t was what? It was L minus x dot L sub x dot. So this, but this is the energy with a minus sign. Because it's the Hamiltonian, right? And So this is the energy. Yes. So this is the energy, right? So this is energy at time 1. Energy at time 1. This is energy at time 0, but I did not mention it enough. But when you differentiate with respect to the left end, the theorem stays the same, except the result with a minus sign. So this is minus the energy at time 0. And so that is 0. And so you see the energy doesn't change from T0 to T1. We didn't even have to write differential equation. I mean, before, in the first lecture and in all the textbooks, you write the equations of motion, and then you write down the expression for the energy, take the derivative of the energy, and use the equations to see that the result is 0. That kind of, in my opinion, hides the real reason for the energy conservation. Here, the energy has the physical interpretation of the force in the t direction. It's the energy is the derivative of the action with respect to t. And intuitively speaking, if this thing was like a slinky and the potential energy doesn't change when you move simultaneously left-right, then your force to the left must cancel the force to the right. It's like Newton's first law, right? For the body to be in equilibrium, the forces must cancel. And that's exactly what it is here. So, except we're not talking about the potential energy of a slinky, but we're talking about the integral of the Lagrangian, but it's just mathematically different, but the particulars are different, but principle is exactly the same. Okay, let me just say very sketchy angular momentum conservation, for example. If you have now, so example 2, now I need X to be 2-dimensional. So you can think of Kepler's problem, for instance, right? So Kepler's problem, or any problem for a particle in the plane, right? So here's time, and here are the coordinates x1, x2. This is the plane, right? So, but to be, so this is, let's say, time t0 and the time t1. And you have point A0 and the point A1. And you have the trajectory, or rather a minimizer of the Lagrangian that I just drew. And let's say the Lagrangian is independent, invariant under rotations around the origin in the plane. That means this whole picture that I drew is invariant under the rotation around the t-axis, right? And you can kind of loosely think of this minimizer as a spring, and the torques at the ends must be equal and opposite, just like in the first example, the forces left-right are equal and opposite. Here, this you have to twist this thing, and the ends resist with equal and opposite torques, otherwise. And that's basically the interpretation of the conservation of the angular momentum. The angular momentum turns out to have the same exact expression as the torque. It's described in the notes that I think are available. So I will not. So don't. I didn't mean this to be understandable, what I just said. I just meant it as a flavor. Okay. So if you read it, you'll or think about it, it then becomes clear that this is simply that. It's just like torque. So in other words, what I found remarkable is that all the things that I knew a long time ago in school, actually, I knew a lot more. I mean, all these things apply almost verbatim to this Hamiltonian situation. Okay. Then I would like to describe Poincare integral invariance. So Okay, so what are the Poincare integral invariants? In the standard exposition, you write Hamilton's equations, which I will not. Well, okay, so you write Hamilton's equations, and X and P are each in dimension n, so it's dimension to n. So you can schematically think of the X as one copy of Rn, and P lives in another copy of Rn. And so in other words, you have this phase space of the Hamiltonian system in which you take any closed curve gamma and let it flow. The flow after time t, let's call phi t is the flow. So after time t, every point on this curve goes to a new place. So we get the image of the curve, and Poincare integral invariant, the first one is simply saying that P dotted with dx over gamma doesn't change. As the curve flows with the flow. Geometrically, this integral is simply the sum of, so if you take the curve gamma and you project, so you can represent this R to n as the product of x1 p1, it's, for example, if it's R4, it's two planes, one plane is x1 p1, the other plane is x2 p2, and the curve is in this space, and you project the curve onto, so let me draw it like this. So this is x1 p1, and x2 p2 is here. So I'm not breaking it up like I did here, but rather I break it up into x comma p planes. So x2 p2. Here's the curve gamma somewhere in our space, and we project the curve gamma onto the first plane, and we also project it onto the second plane, and we add up these areas. They may be negative if you go in the clockwise direction, but you add up those areas, and that's what this integral is. So what the Poincare integral invariant says is that the sum of projected areas doesn't change as the curve evolves with the Hamiltonian flow. Okay, so you see one has to first derive these equations and then prove that the integral doesn't change, which is an easy thing, but nevertheless, it kind of hides why is this happening. It's doing things, the wrong way, but I think too long. So here's the simple immediate reason. So here's our, again, space and time. Again, X could be multidimensional, it doesn't matter. So we have T0, T1, and we're not going to vary T0 and T1, but we are going to vary X0 and X1, right? So we take X0, X1, and look at the action. So because T's are fixed, I'm not putting in the notation. So I look at X0, X1. There is also T0 and T1 in the picture, but they're fixed, so that's not an issue. So how does one prove this Poincare integral invariance if I don't even have the Hamiltonian equations written? Well, all I want to say is that X0 and X1, you see, what I want to say is that this picture defines, let me say it very quickly, this we have this, I probably should have said. We look at X0 and X1 differentiated with respect to X1. That is P1, right, by the main theorem. So S differentiated with respect to X0 is minus P0. Minus is what I had mentioned when you differentiate by the left-hand point. I don't know if I was clear here. So what was the main theorem? It said that the derivative of the action, here it is, the derivative of the action with respect to the second variable is L sub x, which we denoted by P. So instead of x dot, it kind of says something about the slope, but instead of slope, we decide to use the function of slope, which is nicer. Okay, so P basically tells us the slope, but okay. So this contains the entire information. If we have this point and this momentum, think slope, then these equations define this point and this momentum, slope, okay? So let me just say this. So by main theorem, this, and this defines the map from x naught and p naught to x1, p1. It makes sense, right? I mean, if I think of x naught and p naught is given, if p naught and x naught are given, I can solve for x1, right? And then I can plug that x1 into here and I get p1. I'm leaving aside the question if you can solve these implicit equations. That's kind of minor point at this stage probably. So let's call this mapping phi. And now if I take curve gamma in the xp space, in other words, I let x naught, p naught vary, I get the image of that curve. And so I can look at S. So in other words, I can have x naught of a parameter, let's call it lambda. I move the point, so the parameter I call lambda, x naught of lambda, p naught of lambda. As lambda changes from 0 to 1, this point traces out this closed curve of gamma, okay? And so all I have to say is that let's look at x of so this function doesn't change, comes back when lambda goes from 0 to 1, the point x naught and x1 goes back, right? Because I should have said that this maps under phi to another xp. This is the gamma of, this is phi of gamma. Each point maps to the other point, and this point has coordinates x1, p1, both depending on lambda. So S is the cost of, well, not the cost, yeah, S is the action of x naught, x1. And I just want to say that this from 0 to lambda, so as lambda goes from 0 to 1, this does not change. And that is already the statement of the Poincare integral invariance. Why? Because if this doesn't change, I can say, how do I represent the change of the function? So S of x naught and x1, I'm almost done here. From 0 to 1, which I just said is 0 because the point x0, x1 comes back, that's equal to S differentiated by x naught times x naught prime, right? I mean, the change of a function is the change of the, excuse me, I should probably do it a little bit. Is the change, right? I mean, the change of a function as lambda goes from 0 to 1 is the integral of the derivative by lambda, right? But what is this derivative? The derivative is, we differentiate S by the first argument times the first argument prime. plus S differentiated by the second argument times the second argument prime. Prime means with respect to lambda d lambda, integral 0 to 1. But we recognize this, S differentiated by x1, but that's P1 times x1 prime d lambda. And this is S naught is minus P naught, x naught prime. And we recognize this is just integral of P dx over gamma and with a minus sign, and this is integral of P dx over phi of gamma. And that was 0, so that's the proof. Okay, I probably went a little bit too fast, and all I want to say is, if you dig into what I just did, I simply said exactly, almost verbatim, this thing about the slinky. I said that if I hold the two ends of the slinky and then move the hands cyclically in an arbitrary way, bring them back, I did 0 work in total. The work by my left hand is integral of f0 dx0, which x0 is the coordinate of my left hand. And the work done by my right hand is integral of f1 dx1. That's dotted, right? Dx is displacement, f is the force. And that work is 0. And that work is, what is this work? Is the change in potential energy of the slinky. So in other words, I look at the change of the potential energy of the slinky and integrate that from time 0 to time 1, if I do this change during time 1, right? I mean, how S is the name for the potential energy of this thing, right? And I integrate the rate of change over time, and then I get the net change, which is 0, right? So you see, if you look at this proof and the one I just gave, it's verbatim the same thing. And the only addition is that the integral of f dx has a, well, it's the work, but it also has a geometrical interpretation. Whether or not, yeah, it's the same as PDX. Okay. Okay, maybe I want to, I'll skip all the other things, but they are all outlined, they're described in sufficient detail probably in the notes that I sent. Instead, let me just give a quick description of the optical mechanical analogy. Here's a really beautiful thing. So optical mechanical analogy. And I want to say how telescopes and, first of all, telescopes and symplectic map. Optics mechanics and optics and telescopes, symplectic maps. And the telescopes. Okay. So if we look at the in optics, we have the iconal equation, which says that the gradient of time to reach a point from some starting point is 1 over the speed of light. So this is the analog of that is the Hamilton-Jacobi equation. Which says that the function of the gradient of S defined by S differentiated with respect to time plus the Hamiltonian of X and S differentiated by X this is 0. So you see this is very close analogy. And the picture is here is the starting point O. This is the time, the point XY where and we measure the time to get to that point, and gradient of T of XY. And we know that the gradient must be lies on the indicatrix whose radius is 1 over the speed of light. I should say in mechanics, the trajectory is guided by the minimization of the integral of the Lagrangian. In optics, we minimize the time, which is the integral of the distance Euclidean divided by the speed of light. So this is the T of XY, right? This is the time to travel over a curve. Now, in mechanics, I just described the mapping from initial. So here we have map from the initial point and initial momentum, or if you like, velocity, to, so that's at time 0, to the position and momentum at time t. What is the analog in optics? So let me give an example. So let's say you have some kind of an optical device, let's say a telescope, and I actually don't even care what's inside this. I just put a screen before and after, and I send in a ray of light, and let's call this x0, and let's call this position x1. It's a two-dimensional optical device. And let's say I'll call P0 is, well, let's not call it anything yet. P0 is going to be in terms of the angle, but, and the light goes through somehow and comes out at the new point x1, and the time, let's call it S suggestively, it depends on x0 and x1, right? So that how long it takes for the light to go from here to there depends on the location of the 2 points. It's a function of S0, S1. What is the derivative of the time with respect to x1? You see, again, I'm motivated by thought of thinking of this light as kind of a rubber band, which I'm holding by the 2 ends, and I want to know what is the force, and the force with which this rubber band, in this case, it would want to slide down, right? You know what I'm having in mind is, like, I imagine a little ring that can slide up and down without friction only on this line x1, and the rubber band connects to this rubber band to the ring, and in this case it will want to pull it down, right? So I'm asking, what force must I apply to not let it slide down, right? So mathematically speaking, I'm asking, what's the partial derivative of this time with respect to x1? And let's call this P1. So this is just my name for P1. It's a simple exercise to check that, in fact, it turns out to be sine of the angle. So it's roughly speaking the angle, okay? And the derivative of S with respect to the left is going to be, is defined by minus P0. Why do I put minus? Because you see that if I move the x0 up, S gets shorter, right? You see here is, I should do it for like this. This is x0. And if I move it up, I kind of make the distance and the time shorter. So that's why I put minus, and that is minus sine of theta naught. Theta naught. Okay, anyway, so we have this expression, and that allows us, again, if I know x naught and I know p naught, basically I know the point and the angle, that of course will define the point and the angle of the exit. And this is area, this is a mapping phi from x in the space xp. Remarkably, this is an area preserving map. Well, I don't have to reprove it because this is what we had here, right? We already proved that if a mapping is given by the boxed formulas, then it's area preserving. It has a Poincare integral invariant, which is in the two-dimensional case is just area. So here's the area preservation. And what I wanted to say, it got a very nice, simple consequence. So for example, if you have an optical device, like a binocular is like that, but I don't want to know what lenses are inside. All I wanted, so here's the remarkable thing. If you know that the optical device converts a parallel beam of light into a parallel beam of light, but narrower, if it squeezes the beam into a narrow beam by some collection of lenses, which I know nothing about, just knowing this of light, parallel beams. So I want this to be true not just for the horizontal beam, but for nearby beams. If they are all nearby beams, at least, are squeezed, but remain parallel, then this device will magnify. Distant objects. So how does this, how does one explain it? I probably should just say, again, I'll give the flavor of it. What does it mean to magnify an object? Let's say you're looking at the ship far away in the ocean, right? And how do you perceive the size of the ship? It's not really the size of the ship that matters, but it's the angular distance between the front, between the bow and the stern. It's like how much you have to turn your head from looking from the nose of the ship to the tail of the ship, right? That's what matters. So it's the angle between the rays which come from two ends of the ship into your eye. And this squeezing of the beam, if one thing is squeezed, then the other thing has to get bigger. So if the beam gets thinner, then the angle of the beam gets bigger. I mean, this, I'm not giving details, and it's not supposed to be fully understandable. I'm just giving the kind of the flavor, and you can look at the particulars in the notes I sent. So, so because this is an area preserving mapping, in other words, each ray is defined by position where it comes in and at how steep it comes in, right? So if you squeeze all the positions, you know, the beam becomes narrower, then that X gets squeezed, right? From start to end, it gets squeezed. Something else has to expand, that something else is the angle. So in principle, what happens, so if you look at the distant ship through this, so let's say these rays come from the nose of the ship, and they squeeze and they go into a narrow beam like this. This is from the nose, and from the stern there is a small angle because the ship is so distant. This angle is very slightly different, but upon exit, this angle will be enormously increased. And so if you put your eye here, well, the rays come in one direction from one part of the ship and from another. So you will think that the ship is huge, right? That's basically the idea. We perceive size not by size of the object, but the angle between the pencils of rays that come into our eyes. And maybe I will conclude by one remarkable theorem by Gromov. So Gromov's. So I'll state this theorem. So before stating the theorem, I have to kind of summarize what's a symplectic map. Let me just say of R4, it's in the two-dimensional, in the plane symplectic map of the plane to itself is simply area preserving map. So that's simply another word for the old thing, but symplectic map of R4, let's say. And I don't want to, once you have it for R4, it's for R2, and so I want to avoid unnecessary generalities. So the best philosophy is to look, I guess, at the simplest case, which captures the essence and not distract by redundant generalities. So the map from R4 to R4. Is symplectic by definition if it preserves the Poincare integral invariant. Okay, so in other words, if the integral over a curve gamma of PDX, which is equals to integral, does not change for any curve gamma, which is closed and sufficiently nice for the integral to make sense. And here PDX, integral of PDX over curve is, so this is integral of P1 dx1 plus P2 dx2. So you see it's the sum of areas of the projection of gamma onto the two planes. Okay, and so here's Gromov's theorem. No symplectic map can take the unit ball x1 squared plus plus p1 squared plus x2 squared plus p2 squared into the cylinder x1 squared plus p1 squared less than r with r less than 1. Okay, so schematically, I cannot draw a unit ball in R4, so this is the ball in R4, and cannot map it into a cylinder x1 squared plus x2 squared. Oh, sorry, P1 squared. Cannot squeeze it. So this is a little bit like the classical mechanical uncertainty principle. You cannot know the position and velocity of a particle with too much precision at the same time. By the way, I just wanted to say that even here, forget R4, just looking at R2, in this, you see, if you squeeze, you can also think of this kind of an loosely analogous to the uncertainty principle way. You cannot squeeze both. If you squeeze one thing, you unsqueeze the other. If you squeeze the position, you have to unsqueeze the angle. You cannot squeeze both position and angle too much. That's kind of the analogy between uncertainty principle in quantum mechanics and classical mechanics. And I was once at a lunch, and people like Moser and Eisenman and Froelich, I mean, people who understand it better than most anyone in the world, and there was no clarity as to what is actually the connection between these classical and quantum things. It sounds similar, but nobody at the table understood it. So I didn't feel too stupid for not understanding it myself. And okay, so let me give an optical interpretation of Gromov's theorem, okay? Because it sounds so what? I mean, it's a symplectic map. I don't even understand what a symplectic map is, even if I know the definition, I still, so here is the an optical interpretation of the Gromov's theorem. This is a remarkable thing, by the way. I mean, it's 1982, I think. So it's pretty recent, relatively speaking. So imagine you have a screen, and the screen has a unit disk. So I want to interpret a unit. What's a unit ball in R4, right? How do you create a unit ball? Well, you imagine a unit disk, and at each point on the disk emits a cone of rays, and the cone is given by if the point has coordinates x1, x2 in this plane, right? So this is x1, x2. The cone has directions y1, let's call them p1, p2. So p1 and p2 are signs of the angle this way, and this way, this way, right? Let's say, loosely speaking. So p1 squared plus p2 squared is less than 1 minus x1 squared plus x2 squared. Okay, so in other words, the closer to the boundary you are, the narrower that cone is. You see, it's the equation of a unit ball, right? But optically, so the point from the center emits the widest cone of rays. Okay, and then you have two. I should have left some room here, so let me move this thing. Okay. And here we have a slit, a screen with a slit. And the theorem of Gromov says in particular that there exists no optical device. Doesn't matter how smart one is, one cannot come up with an optical device which shepherds all these rays through this narrow slit, and furthermore in such a way that each ray is confined to a dihedral angle. So a dihedral angle like this. So this dihedral angle has aperture, whatever that means, the aperture is less than 1 minus x1 squared. You see, this is still x1. x2, doesn't matter, x2. But the aperture, so aperture is y1 squared is less than, okay? So you take these dihedral angles, I'm sorry, not one, but r. Okay, where r is less than 1. So basically, the details don't matter, but you cannot squeeze the rays in this direction in such a way that their left-right is also squeezed. If you squeeze them, it will force you to not squeeze the left-right. You see, that doesn't follow from the preservation of the volume. And this map preserves volume, but anyway, that was an insight that I don't think anyone else had before. So that's Gromov's theorem. So I was promising to discuss KEM theory, but I don't know if there is time this lecture. When is it over?
Well, you know, we can start. We said we can start. We can stay more. There is no problem.
Maybe I'll just say what the point is. Okay. So I don't have time for a smooth transition from this, but we discussed symplectic maps, and so the simplest symplectic map is the map of an annulus, and I wanted to discuss where it comes from, but since there is not enough time. So let's say we have a mapping of an annulus area preserving map, which twists, for example, the inner boundary by more than the outer boundary. And there is a long history of this. So Birkhoff showed that if you twist the boundaries in the opposite direction, then there exist 2 points which don't move, 2 fixed points. He also showed that, in fact, from this actually, it follows almost trivially that if the 2 boundaries have different rotation numbers, which means average fraction of 2 pi by which they rotate a point, then any rational rotation number is represented by some point in the annulus. So there is some point which rotates at a rational angular velocity, so to speak, which lies between the 2 boundaries' angular velocities. And then with further, so this requires no assumptions except for continuity of the map. It has to be homeomorphism, that's it. If one makes an additional assumption involving a first derivative, for example, it's enough, then in fact, Aubry-Mather, and that was only 1980s, Aubry and Mather independently by different methods showed that every rotation number, not just rational, is represented. So that was a remarkable thing. And okay, so that's under slightly more restrictive assumptions. And then in 1960s, early 60s, so 1962, I think Moser showed that with more restrictive assumptions with sufficiently many derivatives, and if the mapping is small perturbation of the one which leaves circles invariant. So you can look at the very simple map, which simply rotates different circles by different angle. And essentially, the big question that was open for hundreds of years, was probably the central question, was what happens when you make a small perturbation, still keeping mapping area preserving, but perturb it. What happens to these circles? And only in the 60s, Kolmogorov, Arnold, and Moser. So this particular theorem is of Moser's, states that the circles whose rotation number is sufficiently irrational in a certain sense, they survive. Of course, not circles anymore, but under perturbations, they become closed curves close to circle, and they're invariant. In other words, the point, if the image of the circle coincides with itself, and after a change of variables, the circle is a rigid rotation up to a change of variables. And what makes these circles survive is the rotation number is very irrational, which means iterates are very equidistributed. If you rotate the point, after many times you look at the iterates of the point, you don't see uneven gaps. And that kind of allows the averaging to happen. And all I wanted to say, I guess, at this point, that this problem reduces algebraically to this example. So the whole analytical difficulty in proving this remarkable result, which the best brains could not do for hundreds of years, the whole gist boils down to this sample problem. If you can do this problem, then the rest is just icing. So find the function periodic function f of x of period 1 such that, oh yeah, and I should say, given a number omega, irrational number, but find the function such that the second difference, f of x plus omega minus 2f of x plus f of x minus omega, see, it's like a second derivative, but discrete, equals to epsilon, and I'll just say sine of x plus f of x. Okay, so it looks very simple, right? Solve this difference equation. So what I wanted to show, obviously I don't have the time, but I just wanted to say that the question of proving that there exists an invariant curve with the rotation number omega turns out to be equivalent to solving a difference equation. So that's a beautiful thing, that is actually this equivalence between the existence of invariant curve and the difference equation. That was due to several people. Percival was one of them, and I guess Lagrange, you could say. How to solve this equation, that I don't have, I guess, enough time, but I can refer to a short article where it's done. Yeah, and I just wanted to say this is a discrete analog of f double prime equals to epsilon sine of f, right, or something. Let's put it in quotes, but it's like the equation of a pendulum. But instead of second derivative, you have a second difference, and this makes it infinitely harder. So for the pendulum, it was done a long time ago, but this was done only in the 90s. And the last, I guess, the last lecture, I promised to give some counterintuitive examples, which is kind of the most fun, I think. Why is the inverted pendulum stable when you vibrate the pivot point? Is kind of an amazing thing. And some other counterintuitive things about gyroscopic effect and the connection between the spinning top and the Gauss curvature. It's also very simple, and it's kind of surprising that it's not in textbooks, in my opinion. So I will stop.
Thank you very much. Thank you very much once more. So let's thank Mark. So I invite everyone to open microphone to just thank Mark.
Thanks.
Thank you. Thank you.
Thank you.
There are questions?
Sorry, Professor, I believe I have two minor questions. First one is regarding, can you hear me, by the way?
Yes, I can hear you very well.
Okay. So the first one is regarding this last theorem that you mentioned, Gromov's theorem, I believe.
Yes.
That you could have this sort of optical interpretation regarding the Heisenberg uncertainty principle in some sense. And I wonder whether this theorem still holds in higher dimensions as well, or dimension 2. Just, you know.
Oh, you mean Gromov's theorem?
Yeah, if you cannot, just for some sort of, I don't know, physical,
Yeah,
I don't know.
Yeah, you cannot map it from any, the cylinder has to be, so it could be in dimension n.
Okay.
Yeah.
Because I was thinking whether or not you could, you have this sort of questions that you know, physicists are interested in answering, I believe, to some extent. Like, for example, whether we live in a 4-dimensional space and not, you know, 10-dimensional or 24-dimensional. And I mean, this theorem seemed to be some sort of step on the right direction towards answering this in some sense, but yeah, in principle, not really, right? Because I mean, holds in every dimension,
Yeah,
every even dimension, right?
Right.
Yeah.
Right. It's
and the other question,
somebody came up with a proof based on this picture, right? So just, you see, all the proofs that I know, I spoke to Eliashberg, who is along with Gromov are the best experts in this, and it wasn't clear. I think it's not clear to anyone. I think that, for example, to prove it, and from this a picture, to trace the proof on this picture, in other words, that would be really, really interesting, I think.
Yeah, indeed. And sorry, the other question as well was regarding the integral of p dx that you mentioned earlier. That I mean, it wasn't really, it isn't still really clear in my head. What does this integral represent really? If it's some sort of force or energy in the system?
Yeah. So if you look at
I mean, it seems to be conserved as well, right? The theorem that you showed us.
so okay,
very
so
conserved
there are two sides. So first, I guess all I said was, all I meant to say was, you have this action, which depends, let's say, on x and the other x. On the two ends, I don't change t. And we said that s differentiated by x1 is given in terms of the Lagrangian anyway. It's so all I wanted to say was that one can give this P1, that P1 has a counterpart, an analog in statics. That was my main point, right?
Okay.
That P1 has, and that analog is the force for the slinky. It's the force with which your right hand pulls to keep it still.
That makes sense.
And then integral of PDX is, like you said, it's the infinitesimal work that your hand is doing.
All right.
And then symplectic form, I didn't use those words, so the symplectic one form, this is PDX. That's exactly the physical interpretation of the symplectic one form. It's the infinitesimal work that your hand is doing. And in formal lectures, they would say that the integral of the symplectic form, well, that's the total work you did during the motion of your hand. I also didn't have time to say there are these Lagrangian manifolds. What are they? But I guess I don't want to overdose on these things.
That's fine. Okay, thanks a lot.
Sure, but it's good to ask this question. I never put the answer down, actually. What is a Lagrangian manifold? What is a physical interpretation? Okay, that's loosely speaking, it's the manifold around which you don't do any work. Okay, anyway, I will.
Great. Thank you. Thank you, Victor, for the question. Thank you, Mark. So any question, other question? People? No? From Russia, from China? No? I think
That's amazing.
it's late. It's very late.
Yes, yes.
But very nice. We are very happy to have people from so many different countries. Thank you to be here. So, okay, so I think that also Mark has been exhausted because it's true that giving lecture in this visual manner, not to see people in the eyes, is a different feeling. It's a very different feeling.
I'm missing the in-person lectures. I was actually thinking of maybe just pointing the computer at the blackboard and doing it with the blackboards. I wonder if that's not a better way to do it.
I think that is much better to see what you're doing, to see the board, because this is how I was doing before last year. I had the board and I was writing.
Oh yeah, you pointed the computer at the board and did it?
But it's not the people with the vision was not the same. So people voted, the student voted this way.
Oh, really?
I also tried. It worked better. I had a whiteboard, and this was very bad because the light, the computer is try to focus,
Yeah,
and there is the light, and they don't see. But then we painted one of our walls in this ink that is like a board. It was a lot of work here to try to teach, and then it was working. I was teaching with chalk, but for whom was the students that were watching on the phone, they had difficulties. They were not seeing as well. And I gave one lecture on the tablet, and they said, okay, I put them to vote, and it was unanimous. Everyone wanted. For me, it was better.
So they preferred the tablet in the end?
They prefer.
Yeah,
Okay.
because we have students that they are watching from the cellular phone, not even from computer.
Yeah.
So with the cellular phone, they can make it bigger, you know, they can, and it's much, it's much cleaner now, because exactly what she was saying. Actually, Jacqueline was, teaching all of us all this method, the painter, the walling.
Yeah, I experiment a lot in the beginning of the pandemic, what to do, but I tried almost everything. So.
Yeah, so given the situation, this is the best. The people reacted better to write on this. Good notes. We use good notes, but whatever it is, Yeah,
the editor. But the way that you are doing it is the best. You reach the best thing because it's right, and the writing live.
Yeah.
Because when it slides, it's harder. So that's. Took me also time to get to you got to the best already immediately. So after all my experimentation, that's the best way. Given the restrictions, this is the best way.
Yeah, you make me feel better because I was doubting whether I should have used Blackboard, but you convinced me. No.